Sigma and pi bonds. Our goals of this video are going to be to extend our discussion of sigma and pi bonds in order to include the hybridization concepts that we've now covered. We'll be able to identify which orbitals are used to form bonds, including the hybrid orbitals now. And then we'll also get a better understanding of what all of these kind of look like, how they're arranged, what's forming the bonds, etc. So, quick reminder, we have our sigma bonds, which are cylindrically symmetrical, or in other words, they're symmetrical in the same way that a cylinder is, along the bond. These are all of our single covalent bonds. So each time we make a first bond connecting two atoms together, these are sigma bonds. They're freely rotatable. Now with pi bonds, things were a little different depending on if we had one pi bond or two. So if we only had one pi bond, we had a nodal plane, and that was our internuclear axis. So the line that went from our two nuclei, that formed a plane that the sigma bond was symmetrical along. It has two lobes, so one on one side of the plane, one on the other side of the plane. And because of that two-lobed system, this locks it into the place, and so that bond is not movable. It will not rotate. Now, if we have a molecule that has two pi bonds between the two different atoms, or in other words, it's a triple bond, this will be cylindrically symmetrical and freely rotatable. And we looked at why this was in pictures before, and we'll do that again now. So first, let's look at our sigma bonds. Okay, so here I have C2H4. So let's start by drawing that out so we can look at what it looks like. So you may want to pause this a minute and then, check yourself. So we draw this like this. So we have a double bond in the center between the two carbons, and then each one bond to a hydrogen. So we know from our discussion last time that since this carbon has three ligands, 1, 2, 3, and then this carbon has 1, 2, 3 ligands, that both of these are going to need to have 3 hybrid orbitals. And so that makes the hybridization sp2, because we need 3 hybrid orbitals, so we need to start with 3 orbitals originally, which is 1 of an s, and then we have 2 p's, so sp2. Now, what that means is that each of our sp2 orbitals are going to arrange themselves as far apart as possible, and then that's what's going to form all of our connections. That's what's going to bond to our hydrogen and our carbon. So we have these 3 sp2 orbitals, each bounded to a hydrogen's s orbital. And these all form sigma bonds so far. This forms a sigma bond with the s orbital of the hydrogen, same thing here and here and here. And then here we have a sigma bond that's formed by the sp2 orbitals overlapping. Now that we've done this, what orbital haven't we used? We haven't used the other p orbital. Remember, we have 3 p orbitals, and here we've only used 2 of them. So that's what we're going to use to make the double bond. So here I have the molecule tilted a little bit so that we can see the pi bond a little bit better. So this p orbital that would come up here and here, and then the p orbital from the other carbon that would come here and here, those are going to merge together on a side-on-side sort of situation and form this two-lobed structure that is our double bond. So this is our first bond, our sigma bond, and then these 2 purple lobes form our pi bond, or our second bond. Now, let's answer some questions about this. Different ways that I can phrase things. What orbital does hydrogen use to bond with? So in each case, we have a hydrogen that is bonding to a carbon, and it's going to use one of its orbitals to do it. Well, what is the only hydrogen orbital that we have to work with here? The s orbital. Hydrogen has a 1s orbital that only has 1 electron in it, and so it'll use that other space to share an electron with carbon. Now, what does carbon use to bond to hydrogen with? So we have a carbon sitting here, and we have its 3 orbitals. It's bonding to the hydrogen by using its hybrid orbitals, its sp2 orbitals. So we made that hybrid orbital in order to have something to form our sigma bonds with, and so it's going to form all of its sigma bonds with that hybrid orbital. So it bonds to the hydrogen with an sp2 hybrid orbital. So this, and this sigma bond are all formed by the s orbital of a hydrogen overlapping with an sp2 orbital of the carbon. Now, what does carbon use to bond to carbon in the sigma bond? So carbon is bonding to the other carbon in two different ways. It's doing it by using a sigma bond, and it has a pi bond. So for the sigma bond part, these are going to overlap, and so the sp2 orbitals are overlapping. But when we move to go on to the pi bond between the two carbons, now each carbon has its own leftover p orbital, which are going to merge to form this two-lobed pi bond. Okay, so that takes care of our double bond. Now let's move on to our simplest form of triple bond. So we're going to draw out C2H2. So here we have C2H2. Now, what is the hybridization on each carbon here? So it's bonded to two things. Each carbon is bonded to a hydrogen and another carbon. And then this carbon has a hydrogen and another carbon. And so each carbon is going to need two hybrid orbitals. So if we need two hybrid orbitals, we need to start out with two orbitals. And so we need to start out with an s and a p. And so we take that s orbital and we take that p orbital and we merge them together and we form an sp2 hybridized, or excuse me, an sp hybridized atom. Now, what orbitals are left over in that situation? If we've taken an s and we've taken a p and we've made them into sp hybridized orbitals, we have two more p orbitals that are left over. And again, this is going to be the same for each carbon because they're identical. So these two p orbitals are going to be used to make your pi bonds. So here I have a sort of intermediate state drawn out where I show you what it would look like, what you could kind of guess that it would look like. But what it actually ends up doing is a sort of interesting situation where the entire thing merges into one cloud. And you might not necessarily expect that. You would have to be told. So now you've been told. So this makes a cylindrically symmetrical cloud. All right, before we go on to the next step, I want you to remember a few things from the last video, and I want to give you a real brief review so we keep this in mind as we're going through the example. Whenever we start with a certain number of unhybridized orbitals, we get the same number of orbitals back when we hybridize them. So the reverse is true too. If we need a particular number of hybridized orbitals, if we want them, we need to know how many we start with, we're going to start with the same number. Now, hybrid orbitals are a combination of atomic orbitals, and they belong to the atom, and they're still atomic orbitals. Those hybrid orbitals are what's going to overlap to form bonds, and they're going to form our sigma bonds. Different atoms will have different hybridization types, even within the same molecule. You look at each atom separately when you're talking about hybridization. Sigma bonds are going to be made from the hybrid orbitals in hybrid atoms, and pi bonds are made from the leftover p orbitals in the hybrid atoms. Okay, so now we need to decide what kind of hybridization is present on each atom. So first of all, we have this carbon that's bonded to each hydrogen along with another carbon. So it has 4 sigma bonds. Because of that, we're going to need 4 hybrid orbitals. And if we need 4 hybrid orbitals, we're going to need to start out with 4 unhybridized orbitals. So that means that we're going to need an s in all 3 p's. So that would be sp3. Now, let's look at this carbon. This carbon has 1, 2, 3 ligands and no lone pairs. And so since it has 3 ligands or 3 sigma bonds and no lone pairs, we're going to need 3 hybrid orbitals. If we need 3 hybrid orbitals, that means that we need 3 unhybridized orbitals to start with. So we'll start with an s and then 2 p's and merge those together into our hybrid orbitals, forming sp2 orbitals. Now that we have that, we have a little bit of a picture of what's happening in our head. And don't worry, I'll show you a picture in case you don't. So each of these will be forming sigma bonds, and then each of these will be forming sigma bonds, and then the leftover p orbital that we didn't use, that we didn't put into the hybrid orbitals, that's going to bond with oxygen in a pi bond. So now let's look at CH3CHO and look at all the hybrid orbitals. So here is our structure from our last page. Here we have carbon, carbon, and I've labeled them X and Y just so that we can separate them out because they aren't exactly the same carbon. Then we have oxygen here. So I have drawn on here what you kind of want to picture once we've done that last slide, once we've done this and wrote our hybrid orbitals out. We have the CH3 group that's using these hybrid orbitals to bond with hydrogen, and then the other carbon. And we have this carbon here that's using to bond with hydrogen over here, and the carbon over here. So what orbital does hydrogen use to bond with? So, just like before, hydrogen only has a 1s electron that has an electron in it and that has a spot to share an electron, and so it needs to use its s orbital. Now, what about the CX? So here that's going to be the one that has the hydrogens associated with it, all three of them. So here we said that the C right here was sp3 hybridized. So since it's sp3 hybridized, it's using its hybrid orbitals in order to bond to each of the hydrogens. So it's using its sp3 orbitals. Now what about the CY? So this one, the one bonded to the oxygen. That one was sp2 hybridized, and so it's going to use its sp2 orbitals to form each of the sigma bonds. So to this carbon and this hydrogen and this oxygen, it's going to use its sp2 orbital. Now, what does carbon use to bond with oxygen in the pi bond? So here we have a carbon bonded to an oxygen. We have this pi bond drawn out. So it's going to use the leftover one. We used S in two of the P's in order to form the hybrid orbitals, and the leftover orbital here was a p orbital. And so that p orbital is what's going to form our pi bond. Now, I'll make a brief note on the oxygen here. Here I showed the oxygen hybridized. I have the oxygen hybridized with each lone pair and then this in its sigma bonds. And then forming a pi bond here with its p orbitals. But I could have just as easily left oxygen unhybridized and left it as an s orbital with 3 p orbitals and had it forming a p, one of its p orbitals going here, and then the other one's forming the pi bond and having the lone pair in it. So because oxygen has multiple options, either of those are right and either of those would be acceptable. You could say that it was unhybridized and using its p orbitals to form all of its bonds. Or you could say that it was hybridized and using its sp2 orbitals to bond to the carbon with the sigma bond and its p orbital to bond with the pi bond. Either of those would have been correct. Okay, so now a brief summary on what we did. We took our discussion of sigma and pi bonds and now we added in the hybridization concepts. We've identified which orbitals are used to form bonds, including these new hybrid orbitals that we've talked about. Now, hopefully after seeing all of these drawn out, you have a better understanding of what this looks like. Now, as a suggested understanding check before you come to class, find molecules, any molecules, it doesn't really matter, and walk through what we did with CH3CHO. Go through for each one and say, where are my lone pairs? Where are my sigma bonds being formed? Where are my pi bonds being formed? You could take some really big molecules and do this too. Look up any sort of drug that you can imagine, Tylenol, ibuprofen, morphine, anything that you would want that's a big organic compound, and you can walk through and do what we did with CH3CHO for any of those compounds. And that's actually what we'll start doing in class.